Welcome back to Chem 4300. In this video, we're going to cover Chapter 15 on time-independent perturbation theory. Now, in the last few chapters, we solved, or at least we examined solutions to the classical wave equation, as well as solutions to the Schrodinger wave equation for quantum particles moving on various potential energy surfaces. And sometimes those differential equations were simple and had simple analytical solutions like a sinusoid, for example. Other times, that differential equation was not so simple, and to get the solutions we had to, say, go talk to a friend who's a math major to say, oh, I recognize that differential equation and here are what those solutions should be. But what do you do if you run into a differential equation that has no known analytical solution? Well, you can always appeal to numerical methods to solve the problem, and ultimately in this class, when we're looking at the Schrodinger equation for a multi-electron atom or a molecule, that's going to be the only way that you can go, is to do some kind of numerical solution. However, for still a number of problems that we're going to look at, there will be situations where we can find approximate solutions that, for all practical purposes, can still give us reasonably good answers. Now, in this class, we'll encounter a number of such approaches. In fact, in the previous chapter, we calculated a transition rate, and that derivation, which we didn't show, was done using an approach called time-dependent perturbation theory. And it was approximate, but it gave us reasonably good answers. In a later chapter, we're going to see another approach that's called, well, it's called the variational theorem. It's derived from the variational theorem, and we'll use that to get approximate answers for the Schrodinger equation, eigenvalues and eigenstates. Now, in this chapter, we're going to focus on one particularly useful approach that's called time-independent perturbation theory, or it's also known as static perturbation theory. Now, imagine you have some Hamiltonian where we have the Schrodinger equation, h psi is equal to E psi, but we don't have a way to find exact analytical solutions for the eigenvalues and eigenstates. Now, we can use this approach called static perturbation theory to find solutions, provided that we meet a few conditions here. First of all, it will work if we can write our Hamiltonian that we don't have an analytical solution to in a form where it consists of a very large term plus a very small term. So h naught is a big Hamiltonian, and h little is just some small perturbation to that Hamiltonian. The other condition we need is that we know the solution for h naught. We know its eigenstates and we know its eigenvalues. So in other words, we're going to be adding this small perturbation onto a Hamiltonian where we already know the solution, and we're going to try to find an approximate solution for h based on the solutions that we already know for h naught. Okay? So the way we're going to work this out is we're going to rewrite our Hamiltonian in this form here, where we pull out of h1, the perturbation, some variable we'll call lambda, which just gives us the scale of the problem. It tells us how big h1 is, so h1 is relative to h naught. So in other words, it's given by this expression here. And this symbol here means that we're taking the largest eigenvalue of h1 and we're dividing it by the largest eigenvalue of h0. Now, of course, for this to work, we need that lambda be small. So in other words, if lambda's close to 1 or greater, then we're no longer looking at a situation where this is a small perturbation on h naught. But what we want is a solution where lambda is deviating away from 0, where when lambda goes to 0, we know that our solution should go to the eigenvalues and eigenstates of h0. Now, the way we're going to solve this, as you might imagine, based on everything we've done in this class so far, is we're going to do a Taylor series expansion for the wave function and the eigenvalues about a point which is associated with lambda equals 0, where we already know the answer. So a Taylor series expansion for the mth eigenstate of the Hamiltonian is going to be given by this expression here, where this is the eigenstate of the mth eigenstate for the h naught Hamiltonian, and then these are the corrections that we need to work out. Similarly, we're going to do a Taylor series expansion for the energy eigenvalue, and then this is the energy of the mth eigenstate, and this is the energy of the nth eigenstate of H naught, which we know the answer to, and these are the corrections that we're going to add in order to get our corrected energy for our full Hamiltonian. Okay? Now, one of the things I'm going to do is that if you go back to these start to get kind of unwieldy. So I'm going to go ahead and try to replace these with a little bit more compact notation here. So I'm going to take all of those kth derivatives, and I'm going to call these phi. So this is the kth derivative for the nth eigenstate, and this is the same thing here. This is the kth derivative of the energy for the nth eigenvalue. And when I use these definitions, then those expansions become more compact and they look like this. But just don't forget that they're really just represented. This is what we started with, and now we're just writing it a little bit more compactly here. All right, so this is the first correction, the second correction, third correction, and so on for the 0th energy eigenstate, nth eigenstate. Okay. Now, again, when you do a Taylor series expansion, if you have to go out beyond second term here, you probably shouldn't be doing a Taylor series expansion. And the same is true here, that we really are only interested into getting solutions out here to the first couple terms. If we're going out here, then really it's kind of messy, and you really don't want to be doing that. So let's take a look at how we solve this. What we're going to do is take the Schrodinger equation, H psi equals E psi, and we're going to plug all of that into that we have from our expansions into the Schrodinger equation. So here's H is right here. This is our main Hamiltonian plus the perturbation. So that's the total here. For psi, we're going to put in our total expansion. And then for the energy eigenstate, we're going to put our expansion of our energy eigenvalue, sorry. And then for the energy eigenstate, we'll put the expansion for the energy eigenstate once again. So it shows up here and here. So now we have a lot of terms that we're going to multiply out. And one of the reasons I put this lambda, we defined this in such a way that we have this lambda, is the lambda allows us to follow the order of the terms, which ones are associated with the first order correction, the second, third, and fourth, and so on. So if I multiply all of these out and collect terms where I have different powers of lambda, then this is what I find. So there will be some terms that involve lambda to the 0th power, and that will be these terms. And this is just simply the problem without the perturbation present. We already know these solutions here. This equation here comes from all the terms where it's lambda to the 1st power, and this is the equation where lambda to the 3rd power, and you could keep going. Although, as I said earlier, you really don't want to get down to these terms. It really starts to become diminishing returns if you're trying to work out such higher order terms. So if I take let's take this term here, and I rearrange this, and I solve for the correction to the wave function and the correction to the energy, and let's see what you get. Okay. So again, we're going to solve for these corrections in terms of the 0th order eigenvalues and eigenstates. Okay. The full derivation is in the notes, but it's not so bad, and this is what you get here. So you find that the first correction to the energy, the first order correction to the energy, which is simply lambda times that little epsilon, is given by this integral. So this is just a sandwich of H1, the perturbation, inside with the eigenstates of the unperturbed Hamiltonian. So these are the nth eigenstates of the unperturbed Hamiltonian. Here's the perturbation, and that gives me the energy correction to first order for having this perturbation present. So that's pretty simple. Now for the energy eigenstate, then you'll get this solution here. Now this looks a little scary, but it's actually not so bad. Actually, if you look at this, these are the energy eigenstates of the 0th order Hamiltonian, the one we know the solution for. So we know these, and we're trying to get the correction to the mth eigenstate. And these terms here involves the same integral that we saw above, but it also is divided by these the difference between the mth eigenstate of the 0th order Hamiltonian and the jth eigenstate of the 0th order Hamiltonian. And this term in square brackets is just simply a number. It's a coefficient that multiplies times psi j. And so you see that the correction that we get is just a linear combination of the 0th order eigenstates. Add them together and you'll get a correction factor that you add to the 0th order wave function in order to be closer to the right answer for the total Hamiltonian. So this looks a little scary, but if you stare at it a while, you realize that it's not so bad to work with. We'll look at some examples here in a bit. So in a bit is now. So here we see, for example, the harmonic oscillator potential for a harmonic oscillator where we included the anharmicity terms. So remember when we looked at the harmonic oscillator, we made an Taylor series approximation and we ignored all the higher order terms and we had only this term for the potential energy. Now if we add those higher order terms, say the third and the fourth term in that Taylor series expansion for the potential energy, then we would see that there's going to be some changes in the energy eigenstates and the eigenvalues for the harmonic oscillator if these perturbation terms were added into it. So we know the solution to just this. If we add this, how are those energy eigenvalues and eigenstates for the harmonic oscillator going to change? So we're going to write down then that we identify that the 0th order Hamiltonian, in this case, is this term for the potential energy plus the kinetic energy, which we had from before. And now this H1 term will be these two terms, these anharmicity terms that we're going to add in. So we know the eigenvalues and the eigenstates for that Hamiltonian. Remember, the eigenvalues are just this term here, and those Hermite polynomials here were what we needed to make the eigenfunctions or the eigenstates of our H0 for the harmonic oscillator. So to calculate the energy correction, we simply take this guy and we make a sandwich with these wave functions here. So I'm going to take H1, I make my sandwich integral there, and then I plug in the form, which then expanded out gives me these two integrals. Okay? Well, so far I've just left it in terms of the wave function. I haven't put in the Hermite polynomials yet, but you can see that it just becomes two terms there. Now, there were some symmetry rules we learned in that chapter on the harmonic oscillator to help us figure out whether some integrals were 0 or not. So let's try to recall those, because when we look at this, we can see that, I'll make a note here, that this function is an even function, right? This is the ground state of the harmonic oscillator. X to the third is an odd function. So that means that an even function or an even function or an odd function gives us an integrand, which is an odd function. So this integral is 0. Over here, again, we have an even function or an even function. X to the fourth is an even function. So the product of all those even functions is an even function. So that integral will not be 0. So this is what we're left with solving in this problem. So we can just, from simple symmetry arguments, eliminate that one so we don't have to try to deal with it. So now if I go back and I use the form for the 0th order wave function and I plug it in here and here, I get this expression for this integral, and then just working it out with a little bit of math, you should get this result, and then you get the result here for the final energy correction. So here's the 0th order, this is the correction to the 0th order energy. So this is the 1st order energy correction, which you see is going to be, ignores this term, it's just going to be this BF coefficient divided by 32, and then alpha to the fourth, which was just the function the variable that we defined when we solved the harmonic oscillator problem a few chapters back. All right, so that's one simple example where we got the correction to the energy, the 1st order correction to the energy. Let's take a look at if we can get the correction to the wave function. And so we're going to find the correction to the n equals 0 wave function. So again, remember this was the expression that we found for that correction. It's just a sandwich up here divided by the energy difference, forming a coefficient that we sum over all the zeroth order energy eigenstates. So plugging in our perturbation term here, there we get this expression. Okay, so let's just keep going here. Take this and we expand it out into two terms. And once again, we see that we have an even function, an odd function, but now we have psi j. Well, depending upon whether j is even or odd, we may have this integral go to 0 or not, right? So if j is an even function, well, that's even, and odd, well, that's going to go to 0. But if j is an odd function, then we're going to have odd times even. That's going to give us an even integrand. That term is going to stay, and we're going to have to evaluate it, right? Likewise, over here, we have this sum, and we have with involving psi j, and if j is even, and this is even, this one's already even, and that's even, then this guy will be non-zero. But if this is odd, this is even, that's even, then this will go away and be 0. So when this is odd, this term will go away. When this term is, I got that right. Yeah, this one will go away when this one's j is equal to 0. Yeah, sorry. When j is even, this term will go away. And when j is odd, this term will go away. And then you'll have to solve those integrals, which I'll leave for you to do. So let's move on to the second order correction. And that simply looks like this. And again, you can go to the notes to get the derivation of this. But this term right here, you can see, involves the first order correction. So we already looked at that term in the previous slide when we were doing this with the harmonic oscillator problem. But if we take this term, we plug it into there, then you get an expansion like this for the second order energy correction. And now it involves only the zeroth order energy eigenstates and eigenvalues here. So here's our second order correction for the energy. And let's look at some examples of using this one. Okay. So now we look at a problem where we have an electric field applied to a molecule, and it will affect the energies, the energy eigenstates of the molecule. And that perturbation that changes those energy eigenstates will be the dot product of the dipole moment of the molecule with the electric field that it's in. So the perturbation is the changing electric field. As the electric field goes from 0 and gets larger, then we will have a deviation away from some energy eigenstate when the electric field is off. So we're going to compare that to the chapter on electrostatics, where we found the potential energy for a molecule in an electric field, and see if we can draw some conclusions between these permanent dipole moments and polarizability tensor and the results that we get from static perturbation theory here. So we'll write down that the full Hamiltonian is H0, which is the Hamiltonian in the absence of the electric field. So this would be the solution to the full Schrodinger equation for a polyatomic molecule with all the electrons present. We don't need to know what that solution is. We'll just know that we have that solution. And we're going to add a perturbation. We want to know how to correct the energies that we already know based on the presence of that perturbation. So here's what we have in terms of our full form for the potential energy, the potential that perturbs the Hamiltonian. And if we take that perturbing term and we place it into this sandwich to get the first order energy correction, then you see with the explicit form for that it's just simply the negative of this integral, which is the expectation value for the electric dipole moment, with the dot product with the electric field. So this is a vector operator. So this integral here has three components, the x, the y, and the z component, which form a vector quantity. And so this will give us the expectation value for the electric dipole moment for the zeroth order energy eigenstate. So whatever the energy eigenstate, zeroth order energy eigenstate is, it will have an expectation value for the electric dipole moment, and the perturbation in the energies will simply be minus that expectation value, which is a vector quantity, dotted in with the electric field that's being applied, and that will shift the energies up or down depending on the size of this interaction. So this looks very similar. This is the same expression that we had earlier for that first, when we thought about it in the electrostatics chapter without quantum mechanics. We saw that the energy was shifted by this amount. So Only thing we're changing here is that we have the expectation value in this perturbation treatment for that energy shift. Now if we go to the second order term, then you see that we take the same perturbation here and we plug it into our expression for the second order energy correction. So plugging it in, then what I'm going to do is the E field really doesn't depend, it's not an operator, it doesn't depend on anything in here, and I can pull it out to both sides. Now the reason I'm pulling out to both sides will be apparent here in a second. And then I'm going to have in here just the same integral, the integral for the electric dipole moment vector using the 0th order energy eigenstate. So now it's going to be a sum over psi j, psi m for these sandwiches. And this term inside here will be a tensor quantity. So I will evaluate, because this is a vector, I'm going to end up, when I evaluate this, it's a vector squared, I'm going to get a 3×3 matrix. So if you look at this more carefully, you think, well, that looks a lot like what we saw in that electrostatics chapter, where the polarizability tensor gave us the shift in the energy as the molecule polarizes in the electric field. We would get a shift in the energy, which is -1/2 E dot polarizability tensor dot E. So this 3×3 matrix gave us the shift, and we associate then that 3×3 matrix with this second order correction from perturbation theory involving this integral with a vector operator. So if I wrote that down here then for the mth eigenstate, so if I'm looking for the energy, the change in the energy of the mth eigenstate, 0th order eigenstate, then it will be given by this term here, where this is a polarizability tensor that I use in this expression to get the energy correction. And of course that's a tensor quantity, so as you said, this is a vector here. As I said, this is a vector here, so if I do say one of those elements, I say I want to get the alpha xy term, then that's going to be this integral, the mu x integral and the mu y integral, and then you could imagine the same integral for xz, yz, xx, and so on. So you end up doing 9 of these, which you can see that since it's a symmetric matrix, that you really only need to do 6 of them. And these will give you the full polarizability tensor if you know the 0th order energy eigenstates and eigenvalues. All right, great. So that's it for this chapter. And in the next chapter, then, we will start to take advantage of some of these type of perturbation approaches for solving problems.